So hello everybody, this is the One World Mathematical Physics seminar. For those who watch us for the first time, this is a regular bi-weekly meeting of the International Association of Mathematical Physics, which actually always welcomes new members. And our today's speaker is Verch from the University of Leipzig, who will speak about moving away from equilibrium. Please go ahead, Rainer.
Yeah, thank you, Wojciech. Hello to everyone. I should say I'm streaming this from CY Advanced Studies, which is the Advanced Studies Institute of the CY Cergy Paris Université, where I am a research fellow at this time. But this work is independent of my stay here at this institute. And I'm reporting on an article, a recent article, which is on the archive, produced together with Albert Passegger, my student, who actually has the major investment in this article. And it is about something which revolves around the Unruh effect. I mean, this was actually our motivation for this paper. And this paper, which has a different title, is or has become a review article. So it is of some length, 60 or so pages, and more than 160 references. And I now am faced with the difficult task of condensing most of it into a 1-hour talk. Okay, so this was the prefatory remark that goes with it. Okay, so let's come to the introduction. And as I have said, it revolves in some sense or is motivated by the Unruh effect and the question about the character of particles in the context of the Unruh effect. So Unruh has said, and he has also written, that particles are what particle detectors detect. Now, this is sort of a tautology. There is certainly some caveat, and the caveat is that the detector must be up to the task. Such detectors can be quite complicated. Here is a illustration of the Atlas detector that is used at the LHC, and you see it's a very big and very complicated instrument. Now, what Unruh has claimed is to be seen on the background of Unruh detectors, or as they're now called Unruh-DeWitt type detectors, and the related Unruh effect. So the Unruh effect, in simple words, says that asymptotically at late times, a uniformly accelerated detector in point-like idealization coupled to a quantum field in vacuum state will be found in a Gibbs state at a temperature proportional to the detector acceleration. So this part of the Unruh effect is mostly uncontroversial. Maybe one has to allow for the the possibility that the temperature acceleration relation is in part something of a convention. Well, I will not go into details about this point here, but some questions arise. And the important question in some sense, because it has some conceptual consequences and some conceptual underpinnings is the following. Does this mean that a uniformly accelerated detector is immersed in a heat bath of some kind of particles? And is the detector locally in thermal equilibrium with the heat bath and displays the temperature of the heat bath in the sense of the zeroth law of thermodynamics? So is the temperature equality attained purely by the exchange of heat? And in this presentation, I will argue that the previous questions have a negative answer, and I will...
May I ask some question?
Please.
I
Yes.
don't understand what you mean by heat bath, because if you regard the entire universe except for the accelerator as the heat bath, then the answer is surely yes.
Well, I will go into more details what I mean by heat bath a bit later. I think this will become clearer then. Okay, yes, and I'm not talking about the universe at this point. So this is not taking cosmology into account. I will make this more precise a bit later. Okay?
Thank you.
So, anyway, the arguments, or some type of arguments, which I think support the view that the previous questions have a negative answer, stem from the comparison of the following two situations. The first is the constant acceleration motion of a detector coupled to a quantum field in the vacuum state, or a state in the volume of the vacuum state. And on the other hand, the constant velocity motion of a detector coupled to a quantum field in an inertial state, or a state in the volume of an inertial KMS state. Okay, actually it has been noticed long ago that the detectors will behave differently in the two scenarios. And I give you a quote here from a not so well-known article by Sharma, Candelas, and Deutsch, who wrote, for example, the temperature, that is the temperature of an Unruh detector, depends on the acceleration of the observer, and this is independent of his velocity. Thus, two neighboring observers with the same acceleration, but with velocities differing by nearly the velocity of light, would observe the same temperature. There would be no Doppler transformation from one temperature to the other. Or maybe in a slightly more general way of putting it, there would be no blue shift or red shift effects, no aberration effects for the two observers. Okay, and what we wanted to do in our paper is to understand this phrase a bit better, to put it on a more solid mathematical foundation, and thereby corroborate the difference between the accelerated Unruh detector coupled to the Minkowski vacuum, and on the other hand, detectors moving with a constant velocity in a heat bath. And I will make this more precise, as I said, in a while. So I have to supply some notation, some setup, and this is here about algebraic quantum field theory. And actually, algebraic quantum field theory on Minkowski spacetime. So this is all about quantum field theory in Minkowski spacetime, and not on other potentially more fancy spacetimes. And for definiteness, it is also four-dimensional Minkowski spacetime, although much of all of this generalizes to other spacetime dimensions. So if I assume that people working in quantum field theory have some sort of acquaintance with algebraic quantum field theory, so I suppose they have been exposed to this hardcast layer setup in some way. So this here is mainly for fixing notation. So an algebra. What's that question?
Sorry. So you're working the special relativistic frame. That's what is that your setting?
Say again, I didn't catch this.
So your space-time is modeled in terms of special relativity?
Yes.
In this case, every frame is equivalent to one another. So I don't think the notion of inertial frame is well defined in your.
I did not catch this.
I
I
don't
did not
think
understand
the
what you
notion of
said.
if you're working with special relativity, then I believe that the notion of inertial frame is not well defined because every frame is equivalent to one another.
Well, I'm afraid I cannot sort out elementary things here. Please let me proceed and take up such questions at the end. You will see what the framework is. And it's completely standard, okay? So this is really time-proven.
Go ahead, we can come back to this question later.
Okay, so yeah, so we have Minkowski spacetime. This is a copy of R4 with the standard Lorentzian metric. And we have a family of unital C-star algebras, A of O, indexed by bounded open regions in the spacetime. These are the local observable algebras, and they fulfill these conditions of isotony and locality. I think this should be familiar to most people. Then one can form the quasi-local algebra. So this is the smallest C-star algebra, which is defined by all these local algebras generated by them. And there's also an action by automorphisms on this algebra of the proper orthogonal group, such that it fulfills covariance in this form. When there is a state omega on this algebra, then one can pass to the GNS representation, standard procedure, and one can define the induced von Neumann algebras. I hope that using here a different font for them is sufficient to distinguish them from the C-star algebras. And such a state is primary if the induced von Neumann algebra of the quasi-local algebra A is a factor, which means that the intersection of this von Neumann algebra with its commutant contains just multiples of the unit operator. Okay. Now we will be looking at certain one-parametric smooth subgroups of the Poincare group, which have future pointing time-like orbits on a maximal invariant region, invariant under this one-parametric group. We call this region N. And these are here in our contexts either inertial time shifts, so it's just the shift in a time parameter by a time-like unit vector. In this case, you can take as n the full Minkowski spacetime, or it's the boosts Here I take the boosts in the x1 direction. For definiteness, in this case, the region N is the right wedge region, which is depicted here in this diagram. And then the boosts take this familiar form, and the wedge region is formally defined in this way. You could, of course, rotate the wedge, then you get other wedges and corresponding one-parametric boost groups that leave those wedges invariant. But for definiteness, I will just consider this right wedge. Now, I will generally write a alpha up t for the corresponding automorphisms. And if we have a state on the corresponding algebra, then we have the following types of states. We have a ground state. This here is the ground state condition. I assume it's familiar to you. Or we have KMS states, and here I'm giving the KMS condition in its Fourier transformed variant. So you take this correlation function here of two algebra elements A and B. B is shifted around by alpha t, and then you Fourier transform this function, actually in the sense of distributions. And if then this Fourier transform has this behavior, notice that there is an exchange of the order of A and B on the right-hand side as opposed to the left-hand side, then the state is a KMS state. And as I said, this is equivalent to the boundary value KMS condition, and the equivalence can be if you want to know how this works, I recommend having a look at Gartley-Robinson Volume 2, where this is proved. Okay, and then we also have the vacuum state for a quantum field theory in Minkowski spacetime, and it is on one hand, it is invariant by definition under the Poincare group, and it is a ground state for all inertial time shifts. So these types of states play a role in my discussion. So now under general conditions, I should mention the following holds. First of all, KMS states converge to ground states in the limit beta going to infinity. Beta is the inverse temperature, so beta to infinity means temperature to zero. Typically, you need some regularity conditions to establish this. I will not go into details here. And then there's the Bisoniano-Wichmann-Borges theorem, which tells us that, again, under very general conditions, model independent, but actually one needs slightly more than I've stated so far. It says that the inertial vacuum state, which I've just characterized on the slide before, when it's restricted to the observable algebra of the right wedge region, then this is a KMS state at inverse temperature beta equal to pi for the Lorentz boost group, which I had defined before. And this means that in the GNS representation of the vacuum state, the boosts are implemented by the Tomita-Takizaki modular group up to rescaling of the time by the factor 2 pi. This is all well known and very well established. Okay, I shall address now the mixing property and disjointness and all this. And again, unfortunately, I need a little bit of definitions to some of them, to some of you, they will be very familiar, so I apologize if that is now boring for you. For others, it may be new and maybe a bit much to process in the first going. So you may then perhaps want to have a look at our paper and the literature cited there to take this in all detail. Anyway, let us consider two states, omega and sigma, on this quasi-local algebra for the quantum field theory. And one says that sigma is in the folium of omega if sigma arises as a density metric state in the GNS representation of omega. So it can be written in this way, where this rho sigma is a density matrix on the GNS Hilbert space of the state omega. And one says that these two states, omega and sigma, are quasi-equivalent if their folia of states are identical. And that then means, or is equivalent to saying that actually there is a von Neumann algebra isomorphism which transports one GNS representation into the other. In particular, this von Neumann algebra isomorphism is defined on the induced von Neumann algebras. In particular, this psi could be the adjoint action of a unitary. As opposed to the previous situation of quasi-equivalence, one says that omega and sigma are disjoint if their folia are disjoint. There is nothing in the intersection of the folia. And then there's another definition, which is or a property which now follows in the case that these states omega and sigma are both primary, which means that the induced von Neumann algebras in the GNS representations are factors, as I have mentioned. Namely, in this case, the two states are either quasi-equivalent or they are disjoint. So here I have written what it means operationally, that a state sigma is in the folium of omega, then sigma can be approximated by local operations on omega, and this is expressed here. And this is some, important thing if either you have quasi-equivalence or not. If you have quasi-equivalence, then you can say in some sense that sigma is actually something like a local perturbation of omega, because you can approximate it by making local operations on the state omega. Okay, now the mixing property. If we have a state omega on A with the one parametric automorphism group of the type I have said before, so it's either boosts or it's time translations, then such a state fulfills the mixing property if, you look at this correlation here, you have two observables, A and B is shifted by alpha t, and if you take t to infinity, then you have this product of the expectation values of A and B. And this relates to what's called weak asymptotic abelianness, namely, if the state is primary and the GNS vector for the state is separating for the induced phenomenon algebra, then the mixing property is fulfilled if and only if weak asymptotic abelianness is fulfilled. Sometimes this is also called weak asymptotic cluster with respect to this automorphism group. This is apparently at first sight weaker condition, and it is typically fulfilled for time shifts in quantum field theory. In particular, it's defined because of the locality property for shifts in space-like directions. Okay. Now, let's sort of bring these properties to work in some sense. So we take U and V, two linearly independent future-pointing time-argument vectors, and we define the associated time shift groups for them. So one is time shifting in the U direction, the other is time shifting in the W direction, and we usually think these are really distinct directions. So if we have now two states, omega, and they are labeled by U or W, if they are time shift invariant with respect to either alpha U or alpha W, and if the states are primary, the respective GNS vectors are separating for the respective induced phenomenon algebras. And if the states are distinct, so we require they are not the same, and if they fulfill the mixing property for the respective automorphism groups, then it follows that these states are disjoint. Their folia are disjoint, they contain no common element. So they are not perturbations of each other. This says that they are quite remote from each other in their properties. Now, one can apply this. First of all, here comes one corollary, which says that Lorentz transformations are not implementable in primary mixing states. So I formulate this in kind of negative phrasing, namely in the following way: under the stated assumptions on the two states omega U W, whenever there is a phenomenon algebra isomorphism between the induced phenomenon algebras, then this isomorphism cannot connect the GNS representations. This holds in particular for the cases that the state W omega is in fact coming from Lorentz transforming the state omega U by a Lorentz transform which takes U to W, and the potential case that psi is actually implemented by a unitary operator between GNS Hilbert spaces. So this is what maybe in a slightly more specified sense is said that one has implementation of Lorentz transformations, if this would hold, but actually it doesn't under the assumptions I've stated. Now, there is an interesting condition as to when mixing property and primarity, these central two ingredients which lead to this disjointness result, are fulfilled. And that is a spectral property. A spectral property for the automorphism groups relative to the states. So I have to explain this a little bit. So if omega is a state invariant under such a one-parametric automorphism group, there is then a unitary group which is generated here by a self-adjoint operator called L omega, which implements the automorphism group alpha T in the GNS representation and leaves the GNS vector invariant. That is called the Liouvillean. In other contexts, particularly if one has a ground state, it's called the Hamiltonian. But for more general situations, one refers to it often as the Liouvillean. So, and one says that the state and this automorphism group, invariant state, are said to fulfill Koopmanism if the spectrum of this Liouvillean operator is absolutely continuous, except for the single non-degenerate eigenvalue 0. In other words, the only proper eigenprojector with eigenvalue 0 then is the projector on the one-dimensional subspace spanned by the GNS vacuum vector. Well, this obviously there must be an eigenvector with eigenvalue 0, but the statement is there is no other. If that is the case, then omega has the mixing property. And if omega is a KMS state, then it is also primary. So we reach a second corollary, namely, Lorentz transformations are not implementable in KMS states in the presence of Koopmanism if this spectral property for the Liouvillean is satisfied. So then, if the two states omega u, respectively w, that we have been considering before, are KMS states for time shifts in different Lorentz frames, if they fulfill Koopmanism, then they are disjoint. So, some remarks here. There is a considerable amount of literature on this, and as I've said, our paper has a long list of references. So please take a look if you're interested in more literature background. Here are only a very short excerpt of this. The assumptions of corollary 2 are typically satisfied for quantum field theory, since KMS states with respect to different time directions are distinct. They have to be different if U and W are linearly independent. This has been shown by Sewell in a series of articles dating around 2008, 2009. There are also related results by Ojima. There are also precursors by several authors, Naunhofer and Tilling, that had appeared previously. There is also another application of this by Buchholz and Ojima, who have used such a type of argument to show that supersymmetry is not implementable in inertial KMS states. Are there examples? Yes, there are examples. The free scalar Klein-Gordon field with its quasi-free KMS states with respect to inertial time shifts, they exist. That fulfills Koopmanism and provides examples. We discussed this example in some detail in our paper. Actually, a similar result to corollary 2 can be extracted from earlier results of Hermann and Takizaki. However, this previous theorem, which I have presented, holds under slightly more general assumptions. And also this, what these slightly more general assumptions are, we discuss at some length in our paper, so I will not go into details here. Now, I had mentioned that one of the motivation for our investigation revolves around Unruh detectors. So I will now have to say what detectors are and how they relate to these results that I have mentioned so far. So what is a detector? So the simplest form of a detector is a quantum mechanical two-level system. Then the observable algebra consists of the 2x2 complex matrices. And it's often very convenient to consider this detector initially in its ground state representation. So the GNS Hilbert space of the ground state is just the C2. And then it is convenient to consider a Hamiltonian operator, which has two eigenvalues. One is E, supposed to be greater than 0, and the other is 0. And then one can also define KMS states for the detector at inverse temperature beta. And it's given in this form. So it's the trace here of e to the minus beta times the Hamilton operator and dividing by the partition function means here multiplying this beta e. Then there's also a dynamics, which one can, without restriction of generality, define in this ground state representation. And it is given by the adjoint action of the unitary group pertaining to this Hamilton operator. Now, every state on this detector algebra is given by a density matrix in a ground state representation. We have a finite dimensional algebra. And so the folia of all states coincide. And if we have any state on the detector algebra, which is invariant under the detector's time evolution, then I denote by LD, potentially with a sigma referring to the state, the Liouvillean, characterized by its defining properties. Okay, this is the detector. Then we have a quantum field, and the most convenient quantum field in this context, and the simplest one, is the scalar Klein-Gordon field. And there is the standard C-star algebra for the Klein-Gordon field. It's the Weil algebra of the Klein-Gordon field. Now I assume some familiarity on your side with the quantized Klein-Gordon field. And I will not go through all the details of the definition of the Weil algebra of the Klein-Gordon field. This is very standard And there are many excellent literature resources which explain this. I can here resort to the situation where we consider a quasi-free state, because the states that we consider are actually quasi-free states, on the Weyl algebra, which are determined by their two-point functions. And then for spacetime regions O, the induced von Neumann algebras generated by, well, Weyl operators, exponentiated field operators in this GNS representation, which are denoted by phi omega f. F is a test function in spacetime, and here, for the case that these operators generate the induced von Neumann algebra for a spacetime region O, these are real test functions which have their support in them. And to say that we have a Klein-Gordon field means that in such a distributional sense, these field operators fulfill, the Klein-Gordon equation. And then actually these e to the I phi omega f are the representatives of the Weyl operators in the GNS representation of omega. And again, if we have an invariant state on this Weyl algebra under a one-parametric automorphism group, in our case corresponding either to inertial time shifts or boosts as before, then we denote by LF the corresponding Liouvillean. Okay, these are the two systems which we have, and now we have to couple them. So, coupling dynamics of detector and field. So, here we assume that the detector and field are both prepared as KMS states, both having inverse temperature with respect to their intrinsic, meaning uncoupled dynamics. So note, initially, the detector has an intrinsic dynamics. Also, the quantum field has an intrinsic dynamics, which can be representing either time shifts in an arbitrary time direction, or could be Lorentz boosts. The coupled dynamics is then defined on the tensor product of the GNS Hilbert spaces of, well, the detector on one hand, the field on the other hand. And now we need an interacting Liouvillean, which describes, well, on one hand, the intrinsic dynamics of the two systems. On the one hand, the detector, on the other hand, the probe. And there must be now some interaction, otherwise nothing interesting will happen. So these here, basically you set up an interaction Hamiltonian. So it's just called Liouvillean now because we are starting from GNS representations, which correspond to KMS states, I should say. So we have here this non-interacting part of the Liouvillean, and now we have an interaction term. The interaction term is given in this form, and maybe the most important bit here is Q. Q is a so-called, well, one sometimes calls it monopole interaction. So we have basically two, in quotes, field operators. One is for the detector and the other is for the quantum field. There is a parameter lambda that you can see here. Lambda greater 0 is a parameter regular in decoupling strength, as you would usually have this in interactions. Now here we subtract Q with the Q sandwiched with the modular conjugations in these GNS representations for detector and field. Remember, they are in KMS states, so this is well defined, and there is a reason for doing this. I will not go into details here. If you want to know more, I recommend you look at the literature on Pauli field Hamiltonians, where basically you see why it's done in this way. So the G, so to speak, a quantum field operator for the detector is Hermitian, and now it's very important that this matrix is Hermitian but has non-diagonal entries which are different from 0, because otherwise nothing interesting will happen. Yeah, and H here, this H appearing in the field operator for the quantum field, is a test function with suitable spectral properties and small support. Small support you want because you want to approximate maybe a point-like detector. However, you cannot basically at this point in setting up this Liouvillean really insert a delta-like function here, because then this is not going to be a well-defined operator. So you can make the support of this H very small, but you cannot make it being delta. Okay, now there are two approaches towards asymptotic behavior of these coupled dynamics. Of course, what we are interested in is the behavior of the detector under the coupled dynamics for large times, starting from some maybe arbitrary, maybe suitable initial state. Okay, so asymptotic detector response rate. This is a perturbative approach to this asymptotic behavior of the coupled dynamics. And the transition probability of the detector passing from the ground state, this here is the ground state of the detector for the internal dynamics, prepared at asymptotically early times to the excited state. This is the excited state for the internal dynamics of the detector. At asymptotically late times, at lowest order in perturbation theory, which means expanding the dynamics of the interaction Hamiltonian in the Dyson series for small lambda in an interaction picture, is given by the following expression. So this is this transition probability. There appears the lambda squared. There appears the this transition factor for the detector, and you see here at this point it would be not so good if G does not have off-diagonal components, because then this factor would be 0. So we have excluded that. And then there is this factor phi e. And the factor phi e is given in this lowest order perturbation theory here as this Fourier transform correlation function, 2-point function actually, for the field which is prepared in a KMS state for the alpha T dynamics. Well, provided we have arranged this, that the quantum field is prepared in this state. And then what one finds is that in the limit where H goes to delta, this function phi e fulfills detailed balance. And detailed balance is, you recognize it, the KMS condition in its Fourier transformed representation. This, you can think of the detector energy difference E between the two levels being tunable, so that, well, you can vary E and test this detailed balance by varying E. And so in the setting, this alpha T corresponds to Lorentz boost, and our initial state for the field is the restriction of the inertial vacuum state to the right Verch algebra. This is actually the Unruh effect. This is the original Unruh effect. That asymptotically one finds this asymptotic detector transition rate having a thermal Boltzmann-like distribution. It actually generalizes to KMS states of the Klein-Gordon field
The
on static
detector must have a
spacetimes.
constant acceleration, right?
Pardon?
So to observe the Unruh effect, the detector should be in constant acceleration.
Yes,
Right.
and constant coupling to the quantum field as well.
Yeah, both. Yeah, but where is
both.
in this case is the detector in the acceleration? I didn't see the acceleration here.
Well, the acceleration is because the dynamics for the quantum field would be the boosts. So that this expression is along the trajectory of boosts.
I thought the boost is represent constant speed.
No, well, it could as well be, but for the moment, I'm discussing the situation where the alpha TF here corresponds to the Lorentz boost. So this is one bit. And this is if the quantum field state is the Minkowski vacuum. This is the original Unruh effect, yeah, in its perturbative setting. Yeah.
Okay.
And then you find this detector transition rate having this thermal spectrum essentially. Well, this generalizes to KMS states of the Klein-Gordon field on static spacetimes. And there are various investigations about this perturbative setting in other spacetime dimensions and so forth. I will not mention this any further. But this perturbative formula for the asymptotic transition rate generalizes also to the case that the quantum field state, the, if you like, initial quantum field state, is a KMS state for this time direction W. This is the heat bath now, the heat bath. And that on the other hand, we take for the dynamics of the quantum field, the time shifts with respect to a different time direction. Yeah, this enters then here. So you can make these differences. Here you put in the KMS state with respect to one time direction, and here in the dynamics you put in the time shifts with respect to a different time direction, right? So you can calculate this also, and this has been done. So for this situation, one finds that this phi E does not fulfill the detailed balance. So it does not have this Boltzmann-like transition rate, has been shown by Costa and Matzes in 1995. And this has been taken as indication that there is no Lorentz transformation law for inertial temperature equilibrium states. And this has been discussed in some length in these papers by these people. Okay, there's another approach for understanding the asymptotic state of the detector. And this is the question if at late times the detector will be found in a thermal, meaning KMS state. And that is related to the thermalization property or return to equilibrium property of the coupled system. So when we have a state omega on the coupled system of observables for detector and field, and if this is a KMS state, with respect to the interacting dynamics induced by this interacting Liouvillean, then the state fulfills the thermalization property if for every state in its volume it holds that under the action of the dynamics, this state at late times approaches this KMS state, this particular one. And there is, again, a very interesting, if you like, far-reaching theory, the thermalization theory, we have called it, maybe it's known under a different name in the literature. The KMS state omega fulfills the thermalization property if and only if omega fulfills coplanism with respect to the interacting Liouvillean. There is a lot of work in the literature on this matter by several people, also in various combinations. We give full detailed references in our paper. Now, the following has now been shown. So for the coupled detector and field, one can show that there's a beta KMS state for this interacting dynamics on the combined detector and field system, which is in the volume of the tensor product of the non-interacting KMS states for detector and field. And this fulfills the thermalization property for sufficiently small lambda and for suitable test functions h. This means then the partial, and also the partial state on the detector side approximates the KMS state of the detector with respect to its intrinsic dynamics, uncoupled, as lambda goes to 0. And this has been established for the following cases. So first of all, if the field state here, field KMS state, is the restriction of the vacuum to the right wedge algebra of the quantum field, in which case beta is equal to 2 pi, because this is the situation where the uncoupled field dynamics corresponds to Lorentz boosts. This is a very nice paper by Biévre and Merkli from 2006, which also has inspired, well, not only this work, but a couple of other works on Unruh detectors in this more mathematically rigorous sense. And the other situation is, for the field state, you take an inertial KMS state, this is a heat bath. And for the dynamics, you take the time shifts in the same Lorentz frame which defines the heat bath, which defines the inertial KMS state. So this corresponds to the detector at rest in a heat bath. Yeah, so we present this result also in our paper. It's actually a variation of results on Pauli field systems, which have been given in the literature, among others by Jakšić and Pile. So the consequence, what does this mean operationally? It means preparing the coupled system at t equals 0 in any state in the volume of this particular state omega, which is the KMS state for the coupled dynamics, evolved under the interacting dynamics. The partial detector state will asymptotically at large times be found approximately in its internal dynamics beta KMS state for small coupling parameters. Okay,
Rainer?
I'm close to the end of my presentation, so
Okay,
if you
okay,
allow me a few more minutes, I think I can finish.
okay.
Okay, so there is something behind this statement, namely that there is such a KMS state for the interacting dynamics, namely return to equilibrium arguments for KMS states under perturbation of the dynamics. And the perturbation here is adding this interaction term to the uncoupled dynamics. So these return to equilibrium arguments establish the existence of KMS states for the interacting dynamics as, if you like, perturbation to the KMS states of the non-interacting dynamics. Well, I think one of the first circle of results on this in rigorous form is due to Araki, and then again there are many more people who have contributed results about this. I should say the property that this interacting KMS states is actually in the volume of this tensor product of non-interacting KMS states for detector and field. This is key. These interacting KMS states, they are constructed as states in the GNS representation of this product states of KMS states for the intrinsic dynamics, uncoupled for detector and field. However, now we have this disjointness result if the non-interacting KMS states are defined with respect to different time shifts, right? And therefore, a KMS state for the interacting dynamics, so to say, with an interaction perturbation of the uncoupled dynamics, let's say the dynamics with respect to one time direction cannot be constructed as a state in the volume of the KMS states for the uncoupled dynamics, where this heat bath state is with respect to another Lorentz frame, so with respect to time shifts in a different time direction, using the RTE return to equilibrium arguments. So it shows one is in a completely different situation here. The return to equilibrium arguments, which have which were the underpinning of these previous results, which I have mentioned, they cannot be used here. So conclusion. So the last mentioned consequence about the disjointness of the KMS states for the quantum field with respect to different inertial time directions strongly suggests that a detector moving with a fixed velocity with respect to, and always locally coupled to, a heat bath of an inertial quantum field KMS state will not thermalize. So it will not approximate the detector KMS state for small couplings. Should this actually occur, we think that would likely require a very specific coupling between detector and quantum field, and is not a general statement for the general class of couplings or so. This then corroborates the contention of Sharma, Candelas, and Deutsch, which I mentioned in the beginning. A detector moving with constant velocity in an inertial KMS state meaning heat bath. For such a situation, one would expect distortion effects, namely blue and red shifts and aberrations, causing the detector at late times to deviate from the thermal equilibrium state it approximates in the heat bath at rest, as we have shown it does. So this behavior is different from a detector moving along boost trajectories coupled to the quantum field in the vacuum state, because the vacuum state is invariant under Poincare transformations. In turn, this corroborates that the Unruh effect is not the same effect as the coupling of a detector to an inertial heat bath, a point of view strongly advocated by Detlef Buchholz with co-authors in a series of papers. And I should end with some remark on, well, a remark about mathematical idealization. So the disjointness of inertial KMS states is an infinite volume effect. KMS states restricted to local algebras of the Klein-Gordon field are quasi-equivalent for bounded open regions O. So this is really in the idealization that you have arbitrarily extended observables at your disposal. Otherwise, you will not see this disjointness effect. I should maybe mention that this is the case. So you see, there is always the question in the background, what is a good mathematical idealization in this situation? Is it is in this case maybe considering observables at a finite extension in space, potentially very large but finite, already a good approximation for seeing the disjointness. Well, I'm not sure if this can be answered in general. Perhaps it can, and if it can, then this disjointness effect really shows that the Unruh effect detector is different from a heat bath. Okay, this was what I had to say. I thank you for your attention.
Okay, thank you very much for this interesting talk. Are there any questions or remarks?
Wojciech, I think there is a question in chat. It was posted.
Okay, yes. Let me read it. So the question is, why does the detector coupling need to be constant? What if it has known the dynamics?
If it has?
Why does the detector coupling needs to be constant? What if it has known the dynamics?
I didn't catch the last sentence. What if it has?
No, known dynamics
Known?
means sort of, yeah, some deterministic dynamics, I think.
What if it has known the dynamics?
I mean, such things have been investigated in the perturbative setting. So, for instance, in this paper by Fuster and company, they investigate, in fact, a coupling which is given by, which is regulated by a cutoff function in time. And they investigate how, depending on scaling this coupling function to a constant function, how the type of scaling is influencing the approach to equilibrium of the detector. and one can say something there. So basically, well, having the coupling, if you like, constant or switched on for the full time is an idealization, but you can replace it by suitable approximations.
Okay, I see. I see that there is a question coming from Kasia.
Well, actually, it's coming from me. Sorry. Well, first of all, Rainer, nice to
Okay. Hello.
Hello, Dan. How
Hi.
are you keeping?
So far, so good.
We're treating him well.
Okay. What's your
Well, thank you.
question?
Yeah, thank you for the nice talk. So if I understand correctly, you've been comparing the Unruh setup to a detector moving at a non-zero speed through a heat bath with respect to well, sort of a non-stationary observer in some sense. But is it really a fair comparison? Because usually people think of an Unruh detector moving to the vacuum as very, very similar to a stationary detector in a heat bath.
Yes.
But your result on this disjointness depends on the trajectory of the detector not matching
it's not matching the time direction of the heat bath. Yeah.
Yes. So, in what sense does this then really corroborate the effect that the Unruh effect is not the same as coupling the detector to an inertial heat bath, but then in a stationary setting?
Well, if you can rephrase it maybe in the following way. You could prepare your heat bath, so to say, on a constantly moving train, right? Relative to your detector. Yeah. This is feasible if you do this with radiation and you think of a large container which surrounds the detector and moves with constant velocity with respect to it. And well, then you see if you are you see there will be an effect. The detector will not approach equilibrium.
Mm-hmm.
But if you do this with the vacuum state, yeah, it doesn't matter if you prepare the vacuum state on the moving train or in the moving sphere, or at rest with respect to the detector. It's the same state.
Yeah.
So there will be no effect on the detector asymptotically. It will thermalize.
Yeah. Yeah, thank you. I see the difference.
Okay, so any other questions or remarks? You can raise your hand or you can just unmute yourself and ask.
Can I ask a simple question? So do you learn anything about the final state of the detector from this kind of disjointness argument and so on?
Okay, unfortunately we don't.
Mm.
Our idea is it may perhaps be something similar to ANS, non-equilibrium steady state.
Mm-hmm.
We are trying to well get a clue on this in the perturbative calculation. So far, our results are not completely conclusive, I must say. For really the asymptotic state of the detector, moving with constant velocity to the heat bath, we don't know. We really don't know. We have no idea.
But okay, so this is a two-level system, right? So your final answer is a density matrix, two-dimensional density matrix.
Pardon?
So this is so you're studying two-level system.
Yes.
So the stationary state, if it exists, is described by 2x2 density matrix.
Yes.
Okay. So when you say it's not a Gibbs state, you mean that there is a off-diagonal element that you don't see in.
Yes, potentially. Yes. I would expect this.
Okay. But actually, this is not directly related to your work, but I'm sort of puzzled why you just stick on two-level system. Because in a two-level system, if your density matrix is just diagonal, then anything can be interpreted as a Gibbs state with suitable temperature. Right?
Yeah,
And if
I
you have
agree.
more than
Maybe,
two,
so you're basically saying this two-level detector system is
yeah,
in a way too simple.
and if you have three-level system, then even if diagonal.
I understand. Yeah, this may be the case. Yeah, maybe two-level detector system is too simple.
But is it standard to only consider two-level system in this field or in this business?
The two-level system, it's done because it's easier to deal with, but many results work for n-level systems just as in the same way. So that's not really a problem.
Thank you. Yeah.
But Rainer, when you say that the detector doesn't equilibrate, you really mean that the combined system of the detector and your quantum field doesn't equilibrate. Do you? Because you look at the joint system, you don't reduce to observables that observe only the detector.
Yeah, it's for the coupled system. Yes.
So it's not really two level. It's not really two level.
So,
level plus.
So yes, the result would actually be to say the combined interacting system does not equilibrate. Yeah.
So do you know anything? What happens when you reduce the state just to observables of your detector?
Well, good question. We haven't thought this through.
Okay, any other questions? Then maybe let me ask a question. I'm wondering how this measurement situation fits into, let's say, measurement theory. Does it fit, for example, into the measurement theory you developed with Fuster? I don't understand it that well, but I have the impression it was more relativistic than this joint system.
Well, morally it does. So, well, how should I say? I mean, we have sort of a model for the Unruh detector also in our quantum field measurement paper. One could understand. Well, in our paper about quantum field measurement, both the detector is also modeled by a quantum field theory. However, if you consider quantum field theory like, I mean, for instance, the Klein-Gordon field, and you take a non-relativistic limit, c going to infinity, then you get a Bose gas, and so I would think in this limit you get something similar, so an infinite level detector, and of course there are then some technical difficulties with all the convergencies, but it's potentially very, very similar to an n-level detector.
Okay. Thanks. Any other questions or remarks? Does not seem to be the case, so maybe let's thank Reinhard again and stop the recording and finish the official part of the meeting. Maybe in the unofficial one there will be still some questions.